Hello, everyone, and thank you for joining today's John Bacall Colloquium. I'm Mark Honhart, Experiment Sports Scientist at SURF, and I'm excited to bring the John Bacall Colloquium to you today. A few quick housekeeping notes before we begin. Today's talk will be about 40 minutes, followed by 10 to 15 minutes of Q&A. You can ask questions live by raising your hand in Zoom or by using the Q&A button. This talk is being recorded and will be available on institute.surf/JBC, as well as on SURF's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf webpage. You can register for all scheduled talks at institute.surf/JBC. We now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. The featured speaker will be available on Slack for up to 30 minutes following the talk for your questions. Now it's my pleasure to introduce today's speaker. Dr. Frank Streeter is an associate professor of physics at South Dakota Mines. His research focuses on understanding nuclear processes in stellar evolution and the origin of the chemical elements. He is a principal investigator for the CASPAR project and has been active at SURF since 2015. Currently, he serves as the chair of the SURF User Association Executive Committee. He was a chair or co-chair of several editions of the Conference on Science at the Sanford Underground Research Facility, COSURF, usually held every other year at the South Dakota Mines campus. He received his PhD from University of Bochum in Germany in 2000. Before he joined South Dakota Mines in 2015, he was a principal investigator for the Laboratory Underground for Nuclear Astrophysics, LUNE, the first underground accelerator facility in the world, located in the Gran Sasso Underground Laboratory in Italy. He has 30 years of experience in working in different underground laboratories worldwide. I'll now turn things over to Dr. Streeter to present to us CASPAR, Astrophysics Deep Underground.
Thank you very much, Mark, for the very nice introduction. And I would like to thank the Institute for giving me here the opportunity to be the second speaker of the John Bacall Colloquium series and present our work about the CASPAR Deep Underground Accelerator. And over the next 40-45 minutes, I will motivate our work and show a little bit about the details and challenges that we face when doing our work with the CASPAR accelerator. But before getting into science, I would like to pay a little bit of tribute to the place where we all working, the Sanford Underground Research Facility, or as it was known, the Homestake mine, and relate that to my own family history and heritage. Between the two pictures here on the left side and on the right side, there are about 50 years and 4,360 miles. So the picture on the right shows me in 1975 in front of coal mine, which was named after the Saint Catherine, and that was about a mile away from the place where I grew up. So being at SURF is something like coming back home, although mining in my area stopped in the middle of the 70s. So now let's go into the motivation for the work that we are doing. So nuclear astrophysics aims at understanding the universe as the place where we live in and how it has evolved, how stars evolve, and all the nitty-gritty details related to that. And an artist has put that in a relatively nice depiction here that is shown the connection between the astronomy, astrophysics, and the nuclear physics. You have the astronomer with their telescope looking into the sky, observing the events in the sky, and you have the nuclear physicist here using their accelerator depicted by a microscope, looking into the world of the small particles. It looks a little bit like that the nuclear physics is looking down on the astronomer, but there's no disrespect intended here. It simply should relate how the macrocosmos intimately is connected to the microcosmos. And I essentially would like to highlight two detailed motivation, which I think are the most important one, at least from my view. One is to understand the stellar evolutionary passes. And here is a graph highlighting this that shows the core temperature of a stellar object as a function of the core density, and you have certain tracks there depending on the mass of the object. This is one for 5 solar mass, 8 solar mass, 15 solar mass, 14 solar masses. And what is evident from this depiction is that there are, depending on the mass, certain burning stages. Of course, every star, every object goes through hydrogen burning. Most of them goes through helium burning, but only a few of the stars, the very massive one, they reach carbon burning and advanced burning stages. So this is very much related to what is the fate of such a stellar object. And this brings us to these very nice photos that we over the last 2 decades get either from the Hubble Space Telescope or from the James Webb telescopes, which show a combination of planetary nebulas or supernova remnants, and understanding the evolutionary passes that helps us to understand these remnants or to classify supernova explosion. I don't want you to read through the details here. There are many, many more details on the morphologies that can be understood once you know more about the stellar evolution in general. However, of course, this is a science which requires a knowledge from a lot of different fields. I always want to highlight that. Nuclear astrophysics is observation driven, and it comes from different sources. You have the space-based telescopes, you have Earth-based telescopes, you have neutrino observatories. All of that puts together the entire picture that moves us forward in understanding our universe. Now, the second strong motivation that I would like to highlight here is that we want to understand the isotopic abundance distribution as we find that in our solar system. And here we have the isotopic abundance as a function of the mass number of the isotopes. So every point here is a certain isotope, a certain stable isotope. And this is the distribution that you find in our solar system. And we observe there a couple of features here. Actually, without a couple of with a couple of exceptions that I will mention in a second, we find a similar distribution everywhere in the universe. It's astonishing that this spans 12 orders of magnitude from the most abundant element to the least abundant element. Then we have 75% hydrogen, 23% helium, and the rest, 2%, that is what makes up all the other elements that astronomers call metals, between carbon and uranium. What is evident here is that light elements, lithium, beryllium, boron, are underabundant. This is an exponential scale on the vertical axis. So you have an exponential decrease up to iron, and iron forms the peak here, while beyond that you essentially have a flat distribution beyond iron. And these are the features that we want to understand with our research. However, we also have to take into account the chemical evolution of the universe, or in specific our galaxy over time. If we look back at the Big Bang, only very few elements were produced there, only the light elements.
What do you mean to say? Sorry, looks like we've lost Frank for a moment. Our crew is working on getting him back. We will be with you here shortly. Thanks for your patience. Looks like we've got Frank again. Sorry about that. We lost him temporarily. Frank, you there?
I'm back. I'm sorry. Seems I lost the connection.
Okay, well, we'll turn it right back over to you then. Thank you, Frank. Can you reshare your screen so that we can see the slides again?
Oh, sorry about that.
And we have gotten notice that some people were having difficulty with the slides refreshing on the screen. So as I understand it, if you leave full screen mode for some of you, that should fix the problem. Was I?
Yep, sorry about this interruption. So the older stars only show essentially the elements up to iron. And if we look at stars in between, so they are metal poorer than our sun, and show some of the heavier elements, while if we look at modern stars, they show essentially the same elemental and isotopic distribution as we observe in our solar system. And all of that needs to be explained as well. So, and when we all put this information again together, then we understand where most of these elements are produced. So we understand the big picture, but of course there are many of the details that are still open questions here. And to understand all the details, we need to talk a little bit about the nuclear physics, which is the key to understand the details here. This is the chart of the nuclei. This is something like the table of the elements for a nuclear physicist. Every square here is an isotope. All the black ones are the stable isotopes. Increasing proton number is on the vertical axis. Increasing neutron numbers are on the horizontal axis, and this goes from hydrogen here on the lower left up to the heavier elements in the upper right. If you have a reaction, for example, a proton capture, that will increase the proton number by 1 going up. If you have a reaction that is a neutron capture, that goes horizontally, and there are many types of different reactions that have different passes here. So understanding a network of reactions is important in any step along the stellar evolution, and that can be extremely complicated. So here there is the example of such a network calculation for silicon burning, so a very late stellar evolutionary phase for a massive star. And every colored arrow here is a nuclear reaction that need to be considered in the stellar model that describes this evolution. Of course, that depends on the scenario that you are in. If you talk about hydrogen burning, then it's more like light reactions here. But so again, this depends on the scenario. So in summary, the stars are our cooking pots of the universe. And my PhD advisor published a book on this. He called that Cauldrons in the Cosmos, published in 1988. I think that summarizes this very, very well. So if we consider a reaction, we usually have two reacting partners in the entrance channel, here listed at 1 and 2, and that leads to the reaction products, here noted at 3 and 4. Can also be more, of course. For example, the reaction of the CNO cycle, which is the nitrogen 14 plus proton. So those are the reaction partners in the entrance channel, and the products are oxygen 15 and a gamma quant, which is produced. Another one is helium 3 plus helium 3. These are the entrance reaction partners, while the products are 2 protons and a helium 4 nucleus. Now, the important quantity here is the total reaction rate. You need a 4-factor for this. This takes care of avoiding any double counting. Then you have the product of the number densities of the 2 reacting partners, and a second quantity, which here is the bracketed quantity, that is called the reaction rate per particle pairs. And this is the integral over the probability folded with a velocity distribution function. We'll say more about that in a second. Then the energy production through this reaction is simply the product of the total reaction rate times the Q value of the reaction. The Q value is essentially the mass difference between the entrance channel and the particles in the exit channel. So this is the key quantity here, this bracketed quantity, the reaction rate per particle pair. That is responsible for the energy production as the star evolves, and also for the change in the abundance of the nuclei that are produced. So if we look at here for this reaction rate, the phi function, this is the distribution of the velocity of the particle in the scenario that we look in, like the stellar plasma in the core of the star. This is usually very well described by a Maxwell-Boltzmann distribution, which is shown here in this graph. And this has a peak at the maximum, the temperature that is given in this plasma situation. And if you put that in, you can describe this in a more calculatable equation as it is shown here. You don't need to remember the details. The second quantity then is the probability for the certain reaction. And to understand this, we need to go a little bit more into the details of a very crude picture of nuclear physics to describe that through a potential model. Usually here we deal with 2 charged particles which try to get close enough to each other to react and combine. So in this fusion, they fill in this potential well here. However, since they are charged, they see the Coulomb wall, the Coulomb interaction of each other. And one particle is running against the Coulomb potential of the other one. So this depicts the incoming nucleus here, which has a certain energy with respect to the target nuclei. And classically, you have a turning point here, but due to quantum mechanics, there is a certain probability that the particle can jump through the Coulomb wall tunnel and get to the other nucleus and form a new one. But this depends, as it is shown here, strongly on the energy. With a higher energy, maybe up here, it's much easier to tunnel through the Coulomb wall. With a lower energy, then the probability is reduced. And this leads to this strong reduction in the probability with decreasing energy. Now, measurements at higher energies with a high tunnel probability are relatively easy, while actually where we want to know that, and the combination, should have mentioned that, the combination of these two effects that leads to the gamma peak, which is shown here. So this is where you want to know it, and this is usually at extremely low energies. Now here's an example that shows the cross-section for the reaction helium-3 plus helium-3 as a function of the energy. This description is not very useful. You do not see a lot of details here. This is a logarithmic scale. So that's why what we use very often is the astrophysical S factor, which simply removes this effect, this exponential decrease to lower energies due to the effect of the Coulomb wall. Now, this reaction helium-3 is one of the key reactions in the PP chain, which produces the neutrinos, which we can use as our spice to understand the interior of the sun. However, this reaction here, helium-3 plus helium-3, is actually the main reaction of the PP chain, the main branch. But this does not produce any neutrinos. So in the 1980s, when the neutrino puzzle that Nita Bacall told a lot in the last John Bacall colloquium, so when this was a hot topic, there was speculation that at low energies for the reaction helium-3, there was a strong enhancement, a so-called resonance in this reaction, which then would boost the PP chain going through this reaction and lowering the neutrino production in the other branches, which then somehow could have solved the solar neutrino puzzle. However, first measurements showed that this was not the case, no strong enhancement here. I don't need to speak about the details, but this was the first successful measurement of the Laboratory for Underground Nuclear Astrophysics, which my PhD advisor started in 1990 at the Gran Sasso Laboratory. So this was the first direct measurement of a reaction in the solar Ganov peak. And there, this already gives you an idea of the count rate. There we had one event over the time period of 2 months at the lowest energy. That's why also the error bars here are so large. So this was a big success. And for my second tribute of the day, I would like to mention John Bacall here, who later, for a different lunar experiment, highlighted in an interview that the lunar experiment, for the first time measuring directly in the Gamow window, is a beautiful experiment, and praising the group of Luna as magically gifted experimentalists. We appreciated very much this support, the continuing support we had from John Bacall. All right, so that means direct measurements at the Gamow windows are essentially desired for all reaction and all scenarios. However, experimentally, they are often very challenging and or not achievable at all. So for most cases, the extrapolation is still the reality. So here I talk again in terms of the astrophysical S factor. Is a linear vertical scale function of the interaction energy. So if you just have a non-resonant process, like in the example before, the extrapolation is very easy. And always take in mind that there is a certain energy range where you have direct measurements, and the lower energy range is only most cases reachable by extrapolation, and that is actually where you want to know the cross-section. It's much more difficult if there are structures at higher energies, like the tails of broad resonances. And again, always take into account that in reality, the measurable quantity is a cross-section that decreases exponentially if you go to lower energies. So the S factor is only a way to visualize the structures that you see here. Then, of course, you can have narrow resonances in the extrapolation region, which might be totally inaccessible through direct measurements and complicate the extrapolation, or subthreshold resonances. So states which are just slightly below the reaction threshold, which can still, through their high energy tails, affect the cross-section above the threshold in the important energy range. So the extrapolations are extremely important, but they are also very difficult. So going down to as low energy as possible is one of the goals, but also measuring at higher energies over a larger energy region to get a good hand on the extrapolation is very helpful. So for the nuclear astrophysicist here, it's like this detective, Sherlock Holmes, looking through a hole in a wall, looking at the tail of an animal, and you might think it's the desert fox, while in reality it is a big lion. So the extrapolation is dangerous and might lead to wrong outcomes if not done properly and not enough data available. So now let's come to the CASPAR experiment itself. We are located the Ross campus of the Sanford Underground Research Facility. So this is in this area here that is highlighted in the red circle, close to the new cavities of the DUNE experiment, LBNF. We are close to the Ross shaft, and here is the closer layout of the Ross campus with the CASPAR cavity highlighted. This was a former machine shop on the 4850 level. It's close to the Black Hills State Underground campus, where we heard that 2 months ago from Brianna, and about 100-200 meters away from the LBNF dune caverns. Here's a three-dimensional graph of the lab itself. Usually you enter here from the right. going into the change areas where we usually change shoes, put our gear down, can enter then the control room where we control the accelerator from while the accelerator is running. The accelerator itself is sitting in this area of the experimental hall behind the thick concrete wall, and then the rest of the cavity is reserved for utilities and also serves now as part of an extended refuge chamber. And there is a second exit here on the north side. We had a first successful campaign between 2017 and 2021. Then we had to mouseball the experiment, pack everything, wrapped it in foil, and this is a picture of how it looked like now almost 3 years ago, when for the first time we could enter again while the excavations of the DUNE experiment were wrapping up. It still took almost another year, or even more than a year, before we could get started on cleaning. But however, now everything with the support of SURF and SURF custodians is a very nice and shiny lab. Here, our two grad students, Abby and Leah, working on the alignment of the system. So this is essentially the look as CASPAR is today and in working conditions. You have here on the far right the accelerator. Here the tank is open for the alignment. This produces the beam, proton and alpha particles with an intensity up to 100, 150 microamps. The beam then passes through the beam tubes, which are under vacuum, through focusing elements, which keep the beam spread small and focused along the beam as it passes through the vacuum tubes. This is the analyzing magnet, which then guides the energy filtered or momentum filtered beam into the second leg of the beam line, and the experiment then is usually here at the end. The fisheye view distorts that a little bit. The angle between the first leg and the second leg is just 25 degrees. And last year, we had our first beam again after the hibernation period. Here you can see the beam on a quartz at the end of the beam line here in the back of this the big picture. If you have a bigger machine, just to give you some idea, if you have a bigger machine, you can also guide the beam into air. This is a relatively old picture in my former lab in Germany, an 8 MeV proton beam guided into air through a very small aperture here. And this helps you to understand why you cannot do an experiment like that in air, because it's simply the energy loss is too large, and the beam only reaches about a meter. However, the intensity is high enough, you can light a cigarette on that, as Klaus Rolf has done in this. I do not encourage people to do that. There's a lot of X-ray radiation which is coming out of this experiment, and we would not do that here. Now let's talk a little bit about the actual real experiment. In principle, it's a very, very easy experiment, and for no other reason than it's just have the slide. I used the reaction magnesium 25 P gamma to highlight that. The ideal case is that you then have reactions in a very, very thin magnesium target here. However, one of the problems is already magnesium has several stable isotopes, and if you want to do it with magnesium 25, you need an enriched target with that. Then, as I said, the experiment is pretty easy. You guide a proton beam on this and initiate the reaction, which in that case produce a gamma ray, and you put the detector there, and the detector registers the gamma rays. This could be a germanium detector, very similar to the germanium detector that Brianna Mount has in the BH underground campus, but it could also be like what we have used often in the past, a big sodium iodide detector, Hector, shown here in the picture on the left-hand side. The beam is coming in from the right. You have the target located inside the segmented detector. So you essentially have a 4-pi coverage. And the advantage of going underground with such an experiment is shown here. The comparison of the background of such a detector on surface, the red curve, and underground, the blue curve is apparent. Very often, our gamma rays have high energies, so they are in this region here where you have a very high suppression of the background. So we want to go to the details here. The problems come up with the beam current. So you have 100 microamps of protons, charged particles. Everyone carries one elementary charge. You can calculate from this back of the envelope calculation at 6 times 10 to the 14 protons. And if you want 1 MeV protons, you can calculate the power that dissipates about 100 watts on the target. So that means you blow away a very thin target essentially immediately. Additional challenges come from oxidization and already mentioned the enriched material. So a more realistic target is a thicker target here. However, a thicker target then also contains contaminations. I already mentioned the oxygen layer that you can have on the surface. All of that can lead to contaminant reactions and background, beam-induced background. But it also leads to energy loss while the beam particles are traveling through the target. And usually you put that on a backing, and you might have interactions at the interface between the material in the target and the tantalum nuclei in the backing. So they are moving forth and back. Now, usually the proton beam has a certain energy, but that is only present at the surface of the target. While the particles move through the target, they lose energy. So at the back of the target area, they have a smaller energy, which means you have different energies at the beginning and compared to the end. So you always integrate over a certain energy period. The ideal case would be you measure at a defined energy, but here you measure an integral over a wider energy range, depending on what is actually the thickness of your target. And that means you need to know the energy loss. I can go into the details here of this, but very often the energy loss at these low energies are not precisely known. So these are some of the data tables that are used to determine that, and you see the spread of the data. So this should simply give you an idea of the difficulties in determining the exact energy in such an experiment. Okay, this is our realistic experiment. And again, as I said, you would integrate a certain energy range here during your experiment, and you need to figure out what is the energy dependence of the cross-section over this range. Very often, what we do is measuring low energy resonances, narrow resonances, which are very small, that do not change the cross section below it very much. They are at a certain energy range, sorry, at that resonance energy. And if your beam energy is below the energy range of this resonance, so the resonance energy, then in your detector, you do not see the effect of this resonance. So what you measure, the yield, number of gamma quants, will be very low. In an experiment, then we increase the energy, so we move the resonance closer to the surface of the target, and we see at that moment the low energy tail of the resonance. And with further increasing the energy, we can move it inside the target, and this increases the yield. Now, if it is fully inside the target, with again increasing the energy, you can move it forth and back, increasing, lowering the energy a little bit, and you will not change the yield very much. So this is what is called a sig target yield, and should ideally lead to a plateau in the registered yield here. And this is helpful to directly measure the resonance strength. However, if we look into most recent example here, studying the reaction lithium-7 alpha gamma, this is such a scan, and you would expect a flat plateau here. This is made with a lithium fluoride target, and from chemistry, you would expect that you have a solid, stable stoichiometry of lithium to fluorine of 1-to-1 over your entire target. But essentially, this traces the stoichiometry through the depth of your target. And you see here, you have more lithium, while in the back of the target, the right-hand side, you have less lithium. Now, one of the other issues that come in here, you do this scan, do a low energy measurement, repeat then after half a day, the scan again, and the same scan looks like this. This simply demonstrates that within the target, you have a rearrangement of the stoichiometry of lithium fluoride from the back of the target to the front. Or in other words, that probably here means that fluorine is moving away from the front of the target into the back. So while doing the experiment, and this is one of the challenges here, is you constantly change the target. So this is not a stable experiment while you irradiate your target. And analyzing these situations is difficult. And sometimes it leads to the fact that one has to throw entire data sets away and cannot use them, because during the experiment, you simply destroyed your target. Yeah, and the entire excitation curve, the yield curve for this experiment, they look like this. This then needs to be transformed into the cross section, and that is the challenge of the analysis. Okay, the last 5 minutes, I would like to summarize the results that we have obtained so far with the CASPAR phase 1, so before the shutdown in 2021. Here, the experiments that we have done are listed, and the grad students who have worked on this. This was regarding Big Bang nucleosynthesis, the reaction lithium-7 alpha gamma that I mentioned. Tyler Borgward worked on boron-11 alpha N, a neutron-producing reaction. Brian Franz studied the important solar neutrino CNO reaction, nitrogen-14 P gamma, and then we moved to heavier elements in the oxygen to magnesium region, where we again mainly studied the neutron producing reaction neon 22 alpha N, and the reaction which removes the neon 20 through neon 20 alpha gamma as the potential source of neutrons for the S process. So these neutrons then fuel the production of heavier elements, which I will not talk about in this colloquium. However, one of the highlights was the reaction oxygen 18 alpha gamma, leading to populating neon 22. This is part of a sequence which transforms material which comes from the CNO cycle to the material which is able to initiate the S process. And as I said, part of that is oxygen 18 alpha gamma. And with the Hector detector that I showed on the previous slide, I was able for the first time, or we were able to measure for the first time low energy resonances of this reaction with unprecedented precision, and define the reaction rate over a broad temperature range, which then goes into stellar model calculations for the production of heavier element. And this was published in 2022 in Physical Review Letters. If we now come to the future plans, here we will concentrate on the first star nucleosynthesis. And what you need to know for that is that the very first stars in our universe were very different. Today, stars are very much like our sun. Even the average stars have even a lower mass than that. But stars, the beginning of the universe, were much, much larger. 100 solar masses or even beyond that were very typical due to the environment of the interstellar medium. So it's still a big question of how you go from producing, from having the hydrogen and helium being present to carbon and oxygen here. Nowadays, stars do that through the triple alpha process, but there might be even a different process which is more promising, which includes the reaction lithium 6 alpha gamma and lithium 7 alpha gamma, and some reactions on boron. And we will study these in more details in the next couple of years. Then the next question is how to connect this area to heavier elements in these very massive stars. We know the standard CNO cycles, and again, the details are not relevant here depending on the temperatures. This goes to the higher CNO cycles here. But the question is how to get out of these cycles once you do CNO cycle. So the question is how to break out through the reaction fluorine 19 to neon 20, and with that then connect to advanced hydrogen burning stages in the neon sodium or magnesium aluminum range. And recently there has been a measurement by a Chinese group which found a significant increase of the reaction rate for this important breakout reaction, which in a sense then might explain also abundances in the calcium region observed in very, very old stars, which so far here, so this on the right-hand side is the predictions from with the data from the Chinese group, while previous evaluation always ended up significantly below the calcium abundance that was observed in this old stars. Yeah, and finally, and I think I don't think I have much time to talk about this here, we will also study nova nucleosynthesis that is related to the evolution of globular cluster stars. But I will drop this here and just say that CASPAR is back in the game. We have several important measurements on our game plan for the next couple of years. The accelerator is ready to go ahead. I hope I could lay out the motivation for doing this kind of experiments and could convince you of some of the challenges that we are facing while doing these experiments, and looking to the future, and hopefully we will have good results soon. And I end with acknowledging all the people who have worked on CASPAR over the last 5-6 years. And with that, thank you very much for attending and for your attention, and happy to answer any questions.
Thank you, Frank. That was absolutely wonderful. It was great to see CASPAR laid out so well like that. So we're now opening up the floor to questions. Please, if you have a question, you can raise your hand in Zoom or submit it to the question and answer function in Zoom. And while we're collating those, I have a question, Frank, more of a general nuclear astrophysics question. But you mentioned earlier that nuclear astrophysics is itself a field composed of parts of other fields, and we work with a lot of other groups, observationalists and theorists, etc. How is it exactly that the data that is generated from CASPAR is useful then for the observers and the theorists? How do they use that?
So what we measure are the cross sections. So this is essentially one parameter, one important parameter that goes into a full stellar model calculation. There are also a lot of other parameters like opacity, radiation transport, luminosity that go into this model as parameters, but only with a full set of all the parameters you can really describe how a star works. So all the cross sections that we measure go into the full network. And as I said previously, a lot of the parameters that are present there are just based on extrapolation of higher energy data. There are some reactions which are more important than others. These are then called the so-called key reactions, which really have a dedicated impact on what is going on. The really complex thing here is that changing the cross-section would change the energy production and change the reaction products, the abundances as an output, which then in turn changes again the environment that this happened in. So there is a strong feedback between the reaction itself and the environment that it acts in. So this can only be understood in a full simulation. Very often it's impossible to do some hand-waving arguments about how that works.
Thank you, Frank. I appreciate that answer. We're still waiting for more answers to come in the question and answer. And again, if anyone has any questions, raise their hands. We have another question. We're going to go to them live? Jose. All right, Jose, we'll unmute you if you'd like to ask your question.
Yes, hi. Thank you very much for this extremely interesting talk. With regard to the changing composition of your lithium fluoride target, that's a fascinating result, which presumably is mitigated by the heat of the beam on the target. I know a pure lithium target is probably a very difficult thing to actually produce, but is it not possible maybe to do that?
Yeah, the pure metallic lithium
We've been talking a lot about this lately.
that oxidizes quickly. So transport in that case is the real issue. So the problem is very old. So people are suffering this since at least 30 or 40 years. There were measurements in the 80s studying different topics. Lithium and fluorine are always issues. And this is the creating the target, the right target is a science by itself. And it's very much like alchemy, trial and error.
Yes, absolutely. It certainly is alchemy. Yes. Thank you.
Wonderful. Thank you, Jose. We have another question from the chat. Ibrahim asks, what are simulation tools available to study these nuclear astrophysics reactions? And can you recommend any textbooks for experimental nuclear astrophysics?
So for starters, as a textbook, I think a very good read is the Cauldrons in the Cosmos by Klaus Rolf. This is from 1988. It's not the most updated one. There's also a newer one by Christian Eliades called The Nuclear Physics of Stars, which is more technical, more equations. So for a beginner, I always would recommend the Cauldrons in the Cosmos. So about simulating tools. So from the astrophysical point of view, there are open source codes which can be used to simulate stellar evolution. One of them is the MESA code, MESA. That can be essentially used, downloaded by everyone. Then there are other codes by an Italian group, Franic, I think is that code. And yeah, so simulating the nuclear reaction itself is very difficult because then there you have if you want to start here from first principles, there are simply too many parameters. I think one can calculate a couple of the light elements since a couple of years, but this is very challenging for theoreticians. So the extrapolation based on higher energy data is probably still the best path forward, even today.
Wonderful, thank you. So we have a few more questions. We're going to address two more before we need to end. But if anyone has any more questions after we end the Zoom here, you can meet us on Slack and we will discuss those questions there. So two more questions, Frank. One comes from Jarrett. He starts with, great talk on very compelling science. He asks, can you mention the connection of CASPAR to recent James Webb Telescope data regarding the early star formation?
Yeah, this is mainly related to the measuring the lithium-7 reactions. So, as I mentioned in the talk, we are still lacking a little bit the understanding of how the first stars really produce their energy and were working. As I said, that were very massive stars which burn through their material quickly. But we still lack a little bit in understanding, in reproducing the elemental abundance that we see in the oldest stars that we observe in our galaxy. In our galaxy, and also doing spectroscopy on very young galaxies now accessible through the James Webb telescope. So all of that is very complex, and probably an astrophysicist or an astronomer can talk more about this. And as I said, it's not easy to make hand-waving arguments. You need a full simulation for a full understanding of the entire picture.
Well, thank you, Frank. It seems we're out of time, so we will save that one more question for the Slack chat. I see Chad asked that question. We have a couple of more questions out there. So please, everyone who didn't have a chance to have their questions answered, join us in the Slack chat after the chat, and we will discuss those things there. So thank you so much, Frank, for your time today, and we will see you in Slack here shortly afterwards. And thanks, everyone, for attending. A reminder that today's talk will be available to view and share on institute.surf/JBC, also on YouTube and Vimeo. And then a reminder, next month's Deeper Talk will be on May 13th at 9 a.m. Mountain Time. The topic is DUNE, Infrastructure Milestones and What's Ahead, with featured speaker Dr. Sunny So. As a reminder, please join us on Slack right after this talk to continue the conversation with Dr. Streeter and others. The link will be posted in the chat here on Zoom. Finally, we value your feedback. Please take a moment to complete the short survey you'll receive in Zoom you'll receive in Zoom and by email. Your suggestions on future speakers and topics help ensure that this series remains relevant and useful to the community. Once again, thank you all for joining us today, and thanks again to Dr. Frank Streeter for your time to tell us about CASPAR today.